Okay, sorry for the siren in the background if you can hear it. I've been waiting for it to end and it is never ending. But maybe it's fitting for this paper that I'm overviewing because it is quite alarming. The paper is Parametric Statistical Methods Be Trusted for fMRI-Based Studies by Eklund, Nichols, and Knudsen. And hopefully you've heard about it. It's been making its way around Twitter and Facebook quite a bit recently. Yeah, and so basically what this paper is doing is they've run a ton of simulations to evaluate what the actual type 1 error rates of the thresholding strategies we're using in our software packages are. So to make sure, if you really want to fully understand this paper, actually if you've already gone through the summer cram session videos that I've posted, you're pretty well set up for this, I think. So if you're already familiar with the difference between cluster-wise and voxel-wise thresholding, those are two specific things that they look at here. And if you know the difference between parametric and non-parametric thresholding strategies, because this ends up being the biggest distinction in terms of quality of results. If you're not familiar, if these questions, if you don't understand them at all, you can revisit these videos. I will try seeing if I succeeded in putting little click-throughs on these little images, so you could go directly to those videos. But I had quite a few on parametric and non-parametric thresholding, so that would get you up to speed to what this paper covers. Also, how do the software packages differ in how they model group data? So that becomes an issue as well. And to understand that, you can visit this mixed models video. And again, hopefully, if all goes well with my YouTube skills, you should be able to click on this and get to that video. All right, quick review. How do we threshold our maps? What statistics do we choose? Remember, we either can focus on cluster-wise inferences or voxel-wise inferences. So those two types of analyses are considered in this analysis, or in this paper. Also, how do we compute the p-values for our statistics? You can use random field theory. That's typically what people do because the software just automatically, at least SPM and FSL, will automatically kick out those maps typically with the default settings. And you can also use non-parametric or permutation tests. So recall some of the assumptions of random field theory, at least the ones that I covered. Your threshold has to be high enough that you only have blobs. Your data need to be smooth, and there are more specifications for that smoothness this paper looks into and uses to explain some of the results they see. And the smoothness estimate, the Russells, is really important. It's important that that's estimated properly, and it's important that the assumptions hold to make sure the null distribution that we're using, the parametric null, actually matches the null of the data, because that's where the p-value is coming from. The assumptions of the permutation test are exchangeability, so whatever you're swapping, you can't be changing anything about the distribution of your data. So the example I used before is you can't swap time points because time points are not independent, and if you shuffle them, it's assuming they're independent. Likewise, if you have twins in your data, you can't just swap subjects in any old way. You have to do very specialized permutation tests for that. And look for Anderson-Winkler's papers about that, twin data. But that's pretty much it. The only downside is they don't work well with small sample sizes because you can't generate enough permutations to sample the tail of the distribution well. And we need the tail because that's what we're using to compute the p-value. So the basic idea of this paper, if you ever want to test the null, what you have to do is create data that don't have any, doesn't have any signal. And then you just apply your thresholding strategy and you look at how often or how frequently you reject the null hypothesis. So since there isn't any signal in the data, that should happen, I don't know, you tell me, say it in your head. What percentage of the time should you reject the null if the data are in fact null? Okay, well hopefully you're like 5%, because if you're using a 5% threshold, that's what you should see. Of course, with the family-wise error rate, hopefully you recall that's one of the more stringent thresholding strategies, but family-wise error controls the probability of having any false positives. So effectively that means your type 1 error is the number of studies with any false positives divided by the number of studies. So it's not computed over voxels, but it's computed over studies. So you can review the family-wise error rate video for more on that. So how do they do this? They use resting state data. So it's resting state data, there shouldn't be any task. And then they just pretended there was tasks. So they considered these 4 paradigms, 2 block designs, 2 event-related designs. The first block design had 10 seconds of activation followed by 10 seconds of rest. The second was 30-30. The event-related design had 2 seconds of activation followed by 6 seconds of rest, and the other one covered 1 to 4 seconds and or 3 to 6 seconds. So you can read the paper for the details, but generally they looked at a variety of blocked and event-related designs. What software did they consider? Basically the big ones. SPM, and recall this is just an OLS model, and FSL's Flame 1, which is what FSL recommends and what I've recommended before. And just a quick review, the lower level variances are used and a between subject variance is estimated. I'm mentioning this because it turns out this between subject estimation explains some of the behavior that we're going to see in FSL's Flame. So whereas SPM, if you recall from the earlier videos, it's basically a one sample t-test. It assumes homoscedasticity across your subjects, and it's not estimating separate within and between subject variances. But it turns out when you're just trying to estimate a between subject variance by itself, adjusting for the within subject variances, it's a little tricky. FSL also has an OLS option. It's basically SPM a la FSL, but you'll see they're not equivalent. There are always differences in how the data were pre-processed up to this point, and differences in how their smoothness estimators work and other issues. AFNI's OLS is also considered using the 3D t-test. And oh, I totally forgot one. The MIMA algorithm is also considered using AFNI, and a permutation test. The permutation test, I believe, used the first author's program Broccoli, which I will mention again later. So here, before I throw a bunch of graphs at you, and I guess a spoiler alert because I put uh-oh at the top here. So they're using, if you've ever worked with the this resting state data, the Cambridge data is one of the data sets. I've used this one before. It's nice because it has a lot of subjects in it, so you can do things like this. So they faked a 2 sample t-test with 20 subjects. They used a cluster forming threshold, or cluster, the D must be determining threshold, of p equal to 0.01. This, by the way, is the default for FSL. I believe SPM uses a higher threshold by default. And then over here, we're going to have our family-wise error rates. We're going to have those 4 designs, the 2 blocks and the 2 event-related designs for each software package, so, and each approach within the software packages. Varying levels of smoothness were considered. So dark blue is 4 millimeters all the way up to 10 millimeters. And again, this default varies by software. I think SPM's default is 8 millimeters and FSL's is 4. And I'm sorry, I don't know the, I don't use AFNI as often, so I'm not as familiar with the defaults. The black line is our goal. So that is, remember when I said, what should it be? And hopefully in your head, you're like 5%. The goal is going to be this black line, and then 95% confidence interval around that goal was also constructed. So our hope is that the method that we've been using for years, whatever that may be for you, falls within the dotted lines about the black line. All right, so ready? Here comes a bunch of pieces of spaghetti. Okay, so firstly, you can see a lot of methods aren't doing well. So let's focus on the ones that do okay. So the permutation test, this is a theme that will repeat itself throughout this paper, does really well. It's very close. It's definitely within the 95% confidence interval. Flame 1 is really conservative. And I'll get back to why that's the case later. It does have to do with that between subject variance estimate. Whereas the other methods are generally not doing well. The type 1 error should be at 5%, and in most cases it's above 20%, regardless of what smoothing level you used. It does improve with more smoothing, and it's worse with less smoothing. I think those are the major trends here. Yes. Oh, yeah. You know what? I don't know. I'm not going to cover this, so you'll have to check out the paper yourself because it's not coming back to me why the OLS for FSL looks like this. It's very spread out according to the varying degrees of smoothness. So my apologies. Trying to touch on most of the things. Okay, so this is the same thing, but with a higher cluster forming threshold. So still the Cambridge data, still a 2-sample t-test, still 20 subjects, still a cluster forming threshold of 0.001. And you can see a lot of the methods do better. Flame 1 becomes even more conservative. Permutation test is hanging on. It's doing well. It's not that it's hanging on. It's just a stable approach. And yeah, some of the methods do better than others. It's interesting. I'm sorry, I'm just noticing some of these things now. The blue lines on the bottom here, the blue line tends to be on top. So more smoothness. See that? Okay, anyway. Okay, so this is the second thing to notice is that if you use a higher cluster forming threshold, things are better. And this isn't the first paper to show that. I know Torwager has a paper where he for other reasons than just this, recommends using a higher cluster forming threshold. This is the same thing as the last two slides, but with a different data set. The Beijing data set, still a 2-sample t-test, still 20 subjects, cluster forming threshold of 0.01 on the left and 0.001 on the right. And permutation test, doing great. Everything else behaves about the same. Moving on, so the difference here, I'm just showing all 4 plots again, but Cambridge is the top, Beijing's the bottom. The difference is this is a 1-sample t-test, still with 20 subjects. The left column is a cluster forming threshold of 0.01. The top is 0.001, so the clusters, you're starting off with smaller clusters here because the threshold's higher. So with the 1-sample t-test, everything kind of looks the same. Things get better with the higher threshold, except with the Beijing data, the permutation test isn't doing as great as it was before. It's doing okay with the Cambridge data set, but not as well with the Beijing data. Right, so highlighting that. Still performing the best out of all, so. Last, this is voxel level inference. So this isn't using, not forming clusters, but this is just the voxel level inference. So the slides I had for the presentation on the non-parametric method, all of those results that I showed on brains, blobs on brains, were from voxel level inference. If you recall, because you might be looking at this and thinking, oh, I'm just going to use voxel level inference because this looks fantastic. But if you recall, the results for voxel level inference using the parametric methods, although this is showing that there's a nice, much better control of the type 1 error rate, the power was really bad. Actually, the example I used, Bonferroni, matched the voxel-wise random field theory approach. So that's why this isn't going to be, not to... if you're going to run out and try this really quickly to see if you get better results, I'm willing to bet you're going to have very little activation because the power won't be great. So that is that. Same thing now, repeated as before, but with 40 subjects. So we're back to 2-sample t-test, same setup. Cluster forming threshold of 0.01, cluster forming 0.001, larger sample size, basically the same trends occur. Repeat for the 1-sample t-test. Same trends here as well as the non-parametric method is losing it a little bit. The type 1 errors are not as controlled. Right, and I will refer you to the discussion section. They do talk about this in more detail, and I will let you look at that. I believe the TR was a little different for the Beijing. I believe it was 2 for Beijing, 3 for the Cambridge, And I forget the explanation here. Okay. There's one method that wasn't shown in those plots, and this is one where whenever I read that somebody used this, I cringe a little inside. The idea is to use a cluster defining threshold of 0.001, right? So really high. And then instead of trying to find a distribution so that you can control the family-wise error rate in a specific way, you just use 10 voxels. So this approach, you don't really know the actual type 1 error control, what it's supposed to be, because it's not linked to a type 1 error rate. I mean, all the other ones were, we just saw that they weren't linked very well to the proper type 1 error rate, but we don't even have a comparison. So the graph I'm about to show you won't have that black line. So here it is. Generally, there's no permutation test here. But generally, this is really, really bad. Flame 1, more conservative. I mean, we keep seeing this. So it's basically using the pre-processing from each of these and then this thresholding. I don't even know that this thresholding is available in FSL, this type of thresholding. They use the Beijing data set. This is the 2-sample t-test with 20 subjects. The notable thing is that all the other plots have been topping out at 60%, and for this one, the y-axis goes all the way up to 100%. 60% is down here. So you can see that this is the worst approach at all. I highly encourage you to stop using this if you are, because you're really setting yourself up for hugely inflated false positives. So, yeah. Okay, so then they do this comparison to the theoretical nulls. So the idea here is that the red distribution, we want it to match the blue distribution. The other ones match pretty well, so I'm not showing them. I'm just showing Flame 1 because that's the one that didn't match. The red is the empirical null distribution based on Flame, and the blue is a theoretical null distribution, the Gaussian. So now these are the distributions used to compute the p-values. So if I plot my p-value right here, or my statistics say it's 2, you can see that my p-value under the area under the curve, the blue curve, will be larger than the area under the red curve. What's happening here is the empirical null based on FSL's Flame has a lower variance. So the tails are more thin and the resulting p-values are smaller. So that's why Flame 1 was so conservative. So you might be wondering, well, why is the variance so small? Here's why. So this is I don't know, it's kind of cool. But so as I said earlier, FSL is estimating a between subject variance with knowledge of what the within subject variance is. So basically you have two numbers that are summing together to equal your variance. You know one, you've already estimated it, and you're trying to estimate the second number. So this is really tricky with the variance because we all know variances are positive, right? But it turns out when you're estimating the between subject variance in this way, you're left with a difficult decision because sometimes the model you're using or whatever you're using will imply that the between subject variance needs to be negative. And what FSL did is they just set the between subject variance to 0 in that case. So effectively what that ends up doing is it ends up underestimating the variance because the between subject variance is too small. And they've noted this problem for a while. It's in the original paper on Flame 1. So anyway, that's kind of interesting, and that explains this result. But luckily it's conservative, right? If it were anti-conservative, we would be in bigger trouble. So then they go through the assumptions of Gaussian random field theory a little bit more specifically than I have in the past. So the spatial smoothness is assumed to be constant over the brain, and the spatial autocorrelation has the shape of a squared exponential. So I won't go into how you compute the spatial autocorrelation. It's basically you just compare voxels at different lags according to distance. So these I didn't cover previously in my previous videos, these specific assumptions. So to test these assumptions, they compared the empirical and theoretical spatial autocorrelation functions. I'm showing SPM, they're all pretty similar. And the blue line is the one from, in this case, SPM, and the red is the truth. I don't recall what we're supposed to see with the green, but the point is these are not the same, and they're especially different at larger distances. So the explanation then that they use from this is that this could be perhaps why the parametric methods work better with higher thresholds. My understanding of that would be that that's because the distribution assumption is better met for closer voxels. If the voxels are closer, these distributions are closer, right? If the voxels are further away, it's very different. So that was my take on that. And this plot looks very similar for the other software packages. Also, let's assume the spatial smoothness is the same across the brain. And the first image we're showing here is where do the false positives occur? So this is again estimated using the resting state data with fake task. And they took the clusters and they just summed them over all the simulations. So this is a voxel count. Each voxel counts how many times that voxel occurred in a significant cluster. So the hope would be that these would just be randomly scattered across the brain, but you can see they're not. There's a stronger occurrence of clusters in specific areas. A little different for different methods. So then this is compared to the spatial smoothness, which is assumed to be constant. And you can see that the edges where the spatial smoothness differs a lot coincide with where these false positives are occurring. So the takeaway from this is that the smoothness isn't meeting the assumptions of Gaussian random field theory, which is increasing the false positives, and unfortunately it's increasing them in a very specific part of the brain. Last, they also looked at real data. I'm going to go through this quickly. So they just compared the first on the left here are the cluster extent thresholds for SPM, FSL flame, AFNI, and the permutation test. And you can see that permutation test has the highest cluster extent threshold, so it's being the most stringent. Clusters have to be big to be significant, and FSL flame's the second highest, SPM's the third highest, and AFNI's the lowest. On the right, we have the ratio of the family-wise error-corrected cluster size p-values for the non-parametric method divided by the parametric. So it would be assumed that the parametric is, all right, these are p-values, so the parametric p-value is going to be smaller than the non-parametric method. So you can see this ratio tends to be larger than 1. We would want it to be 1 because the non-parametric is, I wouldn't exactly say it's a gold standard, but according to the simulations, it's the closest we're going to get. And yeah, so 1 would be down here. And then these are the two cluster defining thresholds. This is the stringent one, the less stringent thing. And this is simply showing what everything else has been showing, is that the p-values are larger by 2 to 3 orders of magnitude with the parametric approach. It's a little better with the higher cluster forming threshold. And again, this is the real data. So what should you do? I highly recommend you start using permutation tests as frequently as possible. And likely you can, and it's probably already part of your pipeline to have the parametric random field theory based approach to run that first. So you could start with that, maybe use a higher cluster forming threshold just to see if there's any hope. And then because the permutation tests do take more time, the randomize is, I can't even think of how long that is right now, maybe a half hour for a single contrast. This is an FSL based, but it's command line, and really all you need is a 40 nifty file that you dump into it, and a design matrix and a contrast, but those are really easy to construct. So randomize can be used basically with any nifty file that you have laying around. SPMD is a MATLAB based toolbox. They're both developed, I think, by Tom Nichols, so they should be pretty similar. Palm is an Octave MATLAB based, and it has lots of extra bells and whistles compared to Randomize. This was developed by Anderson Winkler, so if you've read any of his papers, he does a lot with twin data, so this has a lot of these. Big part of Palm is to deal with that. And then Broccoli, which was developed by the first author of this paper, Eklund, and I hear it's very fast. They explain it's fast in the paper as well. It's much faster than Randomize, and it's what was used in this paper. So hopefully that was a good overview. I tried to go into as much as the paper as I could. I will say it's an easy read. It's laid out so well. It has a kind of a question-answer format of the sections, which I really like, and I think it's really an approachable way to write a paper. And that's it. So thanks a lot. Please join the Facebook group, follow on Tumblr, or follow on Twitter, or all three, and have a great day.